All right, well, welcome to Physics 208. Modern physics is usually what we call it. You guys all know me, so I don't really need to do the introductions. But I do want to talk a little bit over some of the stuff that's going to happen in class in terms of the syllabus and all that and the structure. Um, but for the most part, we don't have to spend a lot of time kind of going into the nuts and bolts of things. Um, Anyway, so why don't we go ahead and actually jump to the syllabus. I'm going to share my screen and show you guys the syllabus and talk a little bit about it. Um, so you guys know how to get a hold of me, right? Email is the best way. All this stuff is pretty much the same as you've seen before. Obviously, our class, it's Tuesday and Thursday from 4 to 6:20. Um, so we'll be together for a couple hours here on Tuesdays and Thursdays. I will be recording the lectures just like with my other classes. So if you ever miss one, you can find it. It will be in the same spot in YouTube. There will be a playlist for Physics 208, so you can go directly to those. But I want to let you know that the labs are actually going to be on campus and they're going to be with Kathy. All right. So that's probably, well, not probably, it's definitely different than you've experienced with physics before. Um, but she's going to be sort of the lab instructor and I'm going to be the class instructor. All right. So in terms of how she's going to operate labs and her timing and expectations and all that, you need to talk to her. We should be, and I don't know if this has happened for you guys yet. Do you guys have 2 Canvas pages for this class? One for class and one for lab?
No,
No?
I
Okay.
don't anyway.
Okay, well, we're trying to make that happen so that there's a kind of a Canvas page for her so she can put up her lab things for you and all that. Um, that way it doesn't have to go through me, if there's one less step, that's a little bit better. So hopefully that will be happening. If not, just plan on going to lab at the prescribed time, which it's Friday morning, right? Like 8:30 or something like that. I'm not really sure since I'm not the one teaching it. I didn't really pay attention to that time. But anyway, so you actually are going to have 2 instructors for this class, but it's just going to be there's the one in here, so that's me, and then the one in lab, which is going to be Kathy. All right, so that's a little bit different, a little bit funky, but it shouldn't really be an issue. Um, just realize that you're going to be seeing somebody different on Friday than me. All right. In terms of my office hours, the student hours, you guys know how to find me. It's all the same from the math class. In terms of the textbook, we're going to continue to use the OpenStax book, but now we're going to move into volume 3. So up to this point, you should have pretty much finished volumes 1 and 2 between the other 3 quarters. And we're going to move into volume 3. All right, so you can still find it in the same place. Go to OpenStax. I gave you the link on the syllabus. And again, you can download it. That's what I did. So I've got a PDF on my computer. Anyway, so that's the textbook. So what are we going to be talking about? Right, so I like here the course description. Topics include relativity, quantum mechanics, atomic, nuclear, and particle physics. All right, so what we're going to talk about, we're actually going to start with optics. And in fact, let me cruise down here to the schedule. You'll see that we're basically just going to do chapters 1 through 11. It's all of volume 3. So we're just going to do volume 3. And you'll notice that the first 4 chapters are all about light. So the first chapter, like what we're going to start talking about today and the rest of this week, we're just going to talk about light, how light behaves, the things it does when it reflects or passes through surfaces and things like that. And then after that, we'll talk about how images are actually formed with mirrors and lenses. And then chapter 3, we talk about interference, which is exactly what it sounds like when light interferes with itself. And then diffraction, which is kind of a really, it's a cool property of light that does all kinds of things for us, like makes it so that UPC scanners, do what they do, right? When you're at the grocery store and they just run your bottle of Coke across the scanner and go boop. It reads that code, it uses diffraction. I see in the chat box, there's a question, do I know if you're gonna have lab every Friday? I have no idea. I have no idea what her structure is and what her plan is. So again, those are gonna be questions you should ask her, or she'll probably let you know. Kathy will let you know on Friday. Anyway, so we're going to talk about light. You'll notice that's the first big chunk, and then we get into modern physics, and it's called modern physics because it's relatively new. Everything prior to chapter 5 was stuff that has been known for hundreds and hundreds of years, right? This is Newtonian physics. The stuff starting in here in chapter 5, this is relatively new, like 100 or so years new, which probably doesn't feel like it's new, but in the scope of physics, it's pretty new. So chapter 5, we're going to talk about relativity, kind of what the deal is with that. And it's definitely related to light. So it's not like it's a completely new topic. And then we're going to start talking about, particle physics, nuclear physics, quantum mechanics, like what even all that stuff means. But it was sort of a revolutionary idea in physics, which helped explain a lot of the quirky, weird things that weren't really behaving the way that they were supposed to. So anyway, so we're going to start in chapter 1 and just work our way through chapter 11. While I'm here at the page, just want to point out, we are going to be having quizzes or an exam every week, with the exception of this week. I'm not going to have anything this first week. And the last week of class, there won't be a quiz or exam because there's a final coming after that. But they're all on the Thursdays. All right, so you can just plan on pretty much every Thursday we'll have something to do. Anyway, so that's what this class is going to be about. We're going to talk optics first, and then we're going to turn our attention to modern physics and look at all that good stuff, like why does radioactive decay happen? Like, what does it mean when something is a superconductor or an insulator? Talk about like why time changes when you move at great speeds, all kinds of really kind of trippy, weird stuff. For those of you who have taken chemistry, we're actually going to start explaining a lot of what happened in chemistry. When you take chemistry, there's a lot of hand waving. Kind of like, think about when you take your first kind of math classes, there's a lot of, there's stuff that's a little bit above our pay grade. We do the same thing in chemistry, but physics, now in this class, we're going to start explaining a lot of it. So for those of you that were kind of curious why chemistry did what it did, you're going to start getting the answers this quarter. All right, so again, what you guys care about here is the grade breakdown. So I've got it set up this way that we're going to have 10% of the grade is going to come from homework, another 10 from quizzes, 15% from the labs. Again, that lab score, all that's going to be coming from Kathy, and I will integrate it into the overall grade, since we don't give a separate grade for labs and class. And then the 2 exams are each 20%, and the final is going to be worth 25%. So pretty standard, kind of what you're used to. In terms of homeworks, every chapter is going to have a homework assignment, and they're going to be due Tuesday night at midnight. So think of it as a weekly assignment. So chapter 1, what we're going to talk about this week, is going to be due a week from today at midnight. So by April 13th at midnight. And then so on and so forth. So you're going to go ahead and write them out, scan them, upload them. Again, PDF format is preferred. And but I'm going to give you the same deal that I give you in the math class. If you do all the homework and you get a score of at least 50% on each one, you're not going to need to take the final exam. If you're happy with your grade at that point, once we're done with everything else, you don't have to take the final. All right, so weekly homeworks. In Canvas right now, I'm working on building the Canvas shell. You'll see that right now there are only 2 homework assignments in there, homework 1 and homework 2. But yeah, there will be more, obviously. There's going to be all the way through homework 11. Quizzes, we're scheduled to have 7 quizzes over the quarter. Again, those are the off Thursdays, the non-exam Thursdays. Of course, we all know that 7 will turn into 6, possibly even 5 by the time we're done, because you know me. But we're set. I'm planning on having 7 quizzes, and really just to keep you up on things. And so we're going to do quizzes kind of the same way as the math class, where you're going to start the quizzes at the beginning of class. So they'll open up on Canvas at 4, and you'll have until 4:40 to upload them. So again, consider that 30 minutes for the quiz and 10 minutes for technology. And I will drop everybody's lowest quiz score. All right, so pretty much exactly the same format as math class, just slightly different times. And then exams are going to be the same deal. They'll open up at 4, but you'll have until 6:30. So 2 hours for the exam, 30 minutes for whatever issues. All right. Okay, so that's how your grade's going to break down. Other than that, same information as before, just all the registration info, DRC students, library, and whatnot. And yeah, there you go. So hopefully that real quick run through the syllabus gave you everything you needed to know. But you guys all know me. You know what to expect. Oh, and I see that Jacob has shown up. Hi, Jacob. Good to see you. All right. So any questions about that at this point, other than questions specifically about the lab that I cannot answer at this point in time? No? All right. Okay, so I actually do have a question for you guys because I wasn't with you in E&M. So you took E&M in the fall, right? Not in the winter?
Yeah.
Yeah, okay. Did you guys complete volume 2 of this book? Did you go all the way through like the electromagnetic spectrum?
Yes.
Yeah. Okay, and I'm not expecting that you remember it all, and I think that there was a little of that behind Bradley's yes, and Ralph putting in the I think so in the box. I know it's been a while, but I kind of figured that it's really natural after you talk about electricity and magnetism separately, and then you kind of put them together and go, hey, look, electromagnetic waves have both an electric field and a magnetic field, and they're orthogonal to each other. Oh, sorry, I used a math term. This is physics class. They're parallel to each other, or sorry, perpendicular to each other. And, depending on the wavelength, we classify them in different ways, right? You've got X-rays and you've got gamma rays and you've got visible light and blah, blah, blah. Okay, so you've kind of seen that-ish. All right, well, we're going to look at in depth at light, at how light behaves, at how it does its thing. And by the time that we're done with these 4 chapters, I think it was 4 chapters, you're going to see that light is an interesting thing because it behaves very differently than other materials. It does things that are unique to light, right? Anyway, so let's just start talking about it. So light is kind of weird because when we say light, we all kind of have in mind what it is, but here's what I want you to do. Try to describe light to me. If we're going to talk about light, what does that mean?
See, that's an interesting question because there's a couple of ways of looking at it.
Like what?
Well, my first thought was visible light. I'm looking at stuff in the room while you're asking the question, and I see different things. That's visible light. But then I also thought about like a laser pointer, or like a heat lamp, like thermal energy.
Okay.
And then
Well,
I thought star.
okay. Well, how about we just start with light? There's light coming through my window, right? There's light coming through my window. But what is light?
I guess by now we can say it's an electromagnetic wave, I guess.
Maybe. I mean, it might be a wave. It's okay. It is a wave. But all right, let's say, okay, let's get out of physics world for a second. There's a 10-year-old kid walking down the street. Comes up to you and he says, oh, so you take physics? Yeah, that's cool. Well, what are you studying? Oh, we're studying light. He's like, well, what do you mean? What's light? How would you explain it to a 10-year-old kid? You're not going to say, oh, it's an electromagnetic wave that propagates, because that kid, you lost him at electromagnetic, right?
Probably what we can see from objects, or how we can see objects.
Okay.
Yeah, I was gonna say something you can see but can't touch.
Oh, okay. Ooh, something you can see but can't touch. Nice. Well, this is challenging, right? Because we all know what light is. We all know what it is.
Communication of information, maybe.
Ooh. All right. Well, is that restricted to light?
I guess it's not because sound, and that's just. Never mind. I retract
No,
my
no,
statement.
no. Don't say never mind. It's just obviously that is something that light does do, right? But it's not necessarily a way that we can describe light specifically, because there are other things that propagate information, right? Like sound is a great example. In this world, you hear me because of light. But if we were in the room together and I'm talking to you, it doesn't require light for you to hear my voice, because that pressure wave, it's going to propagate itself through the air, and it's eventually going to vibrate in your body. Your eardrum's going to catch it and you're going to hear it, right? So yeah, it's challenging, and it's just one of those things that we all know what it is, but trying to describe it exactly is a little difficult. Now, I wanted to bring this up because physicists had the same problem, like from the very beginning. They knew about light. They saw, they saw it coming from the sun. They saw it coming from the moon, from the stars, from fires, and it definitely has something to do with like vision and seeing, right? So like I want to get back to what Victor said. He said something along the lines of, it allows us to see things. And that really is maybe the best thing we can talk about light right now, is in terms of its sensory reception in us, right? Like our eyes observe light. They are designed to observe light, and that's the only thing that they observe. At least I can't think of anything else that my eyes tell my brain about. They might react a little bit to like differences in air pressure. Right? They'll change their size a little bit and all that. But really, our eyes, they are organs that are designed to receive light and pass that message to our brain for interpretation. Right? And no other part of our body does that. And I think that's kind of interesting too. If you just look at how the body is created, that we have things that specifically register certain senses, right? Like taste. It's the mouth. Well, with a little bit of smell. I don't know if you know how much smell plays a role in taste. Did you guys know that I got COVID? I don't know if you guys heard, but I actually contracted COVID back in December. I'm totally fine. But I did lose my sense of smell and taste for a while. And it's crazy how important smell is to being able to taste things. And I don't know that I'd ever actually experienced it to this extent before. But anyway, I digress. So I like the idea that when Victor says it's sort of the thing that lets us see objects. Without light, we would not see anything. Right? That's what darkness is the absence of light. Right? So maybe that's the best we can do right now. That light is the thing in the universe that makes it so that we can see. All right. Well, scientists, of course, got into it, and we're like, all right, well, let's see if we can figure out about it. And it definitely seems like it's a thing, right? Like, think about it. If I have a flashlight, I think I got one. Yeah, I just have a little pen light here, but all right. So I have a little flashlight. You can see it, right? Just turned on and came back off. Now, there's no light. I press a button, light shows up. I unpress that button, light goes away. So it's a thing. It's just like any other thing. It doesn't always exist. It can exist. It can go away, right? But I guess maybe that is a little bit different. Because like this little pen light, it doesn't just like go away. It's always there. But we've seen with things like electricity and all that, that you can turn things on and off. Basically, you can make a current happen. And so you start looking at it like that, and you start going, well, maybe light isn't so much an object as a movement of things.
Maybe like a byproduct.
Yeah, like it shows up when other things are doing their thing, right? Kind of like electricity. Like, think about this. So current, when you actually have current happen, it's not like all of a sudden we made electricity, right? What causes current?
A magnetic field.
Okay, so a magnetic field can make it, but just like at the basics, what is current?
Electrons moving.
All right, so it's the movement of charge, right? So and Victor, you said electrons. It's not always electrons, but it's that there's charge moving, right? So you think about like electricity, it's sort of the result of something else happening. Well, maybe that's what's going on with light. Right now, obviously, this thing itself is when I depress that button, it turns on because I close a switch, which allows charge to move, which then creates electricity. That electricity goes through whatever, and hey, it makes light. Okay, so light isn't really like an object per se, but maybe the result of something, right? Like, think about this. What makes it so that we see light when we're burning a fire? Well, it's the chemical reactions that are coming from the combustion. And so maybe it's just a byproduct of that. So I guess maybe the question is, does light just exist on its own? Is that even a thing? Right? Like we can talk about an electron existing on its own. We can talk about, you know, this pen existing, but maybe light doesn't actually exist. All right, so this is a little troubling. It's not nearly as cut and dry as here's an object, let's study it. But it does exist, light clearly exists. And in this way, it's sort of similar to electricity. Like think about electricity and magnetism. A lot of the stuff that we see from that, it's not like there's electricity, but it's the result of something, and there is such a thing as electric fields. All right, well, as scientists started studying light, the very first thing they tried to determine was how fast it moves, right? And you guys probably all know, what's the speed of light?
3 times 10 to the 8th meters per second.
Yeah, so 3 times 10 to the 8th meters per second. About. It's a little bit under. It's like 2.9996 or something like that, but it's close enough to 3 times 10 to the 8th meters per second. But what they found was that light speed isn't always the same. Sometimes light travels slower than that. And so it turns out that there is this 3 times 10 to the 8th, that speed that we give light, that's actually its maximum speed. That's the fastest speed that light's going to take on, and that happens in a vacuum. As soon as we have light going through something else, right, like passing through my glass of water, right, passing through the air, it's going to slow down. So why do you think that's going to happen? Why do you think it's going to slow down if we're not in a vacuum?
I don't know.
Okay, so Ralph just put in the chat box, refraction and diffusion. Possibly. And we'll actually talk about what those things are in a little bit. And Victor just says, you remember that it's impossible to measure light speed in one direction. What do you mean by that? I don't think I understand what you mean.
I remember seeing someone that measure light is you need to measure the reflection instead of just the light itself from one point from A to B.
Okay. Yeah, I mean, the thing, I think probably what you're getting at there is because it's so fast, it's really hard on the kind of scales that we have to notice or to measure the time difference, right? I'll get back to your comment in a second, Ralph, but let me just talk about this for a minute. So let's say speed of light is around 3 times 10 to the 8th meters per second, right? So, I mean, that's an incredibly large number. That's 300 million meters per second. 300 million meters. So let's say that we're in the chem lab and we're going to set something up so that we turn light on one end of the room and we look for when the light reaches the other side.
Good luck.
Yeah, I mean, let's go, and this is way too big for the chem lab, but let's say it's 30 meters across. It's not. But even if it was 30 meters, and we're doing 300 million meters per second. Okay, so you divide that by 30, that's 10 millionths of a second. It's going to take light 10 millionths of a second to go from one end of a 30-meter room to the other end of it. Okay, your eyes are never going to even notice that. So the fact is that on our kind of scales that we deal with, our length scales, light is so fast that it's virtually instantaneous. And Victor, that's what you're getting at with the mirrors. If you set up some sort of an experiment where you have light bouncing back and forth between a bunch of mirrors, what you just did was you increased the distance that the light is traveling. Right. So again, think about the chem lab have mirrored walls and shoot light towards one of them, so it bounces and back and forth, back and forth, back and forth, back and forth, back and forth. If you can get that angle small enough, okay, now you went back and forth in that room 1,000 times. So instead of only being at 30-meter distance, it's at 30,000 meters. All right, well, that's, for our eyes, it's still going to feel pretty instantaneous, but we're getting to the point now where that's going to allow us to, if we've got good technology, to see the difference in the time. So I think that might be what you're getting at with what you're remembering, Victor. And that is one of the things that they used back in the day to help them get an idea of how fast light was moving, was mirrors to increase the length. But if we get back to my question about why it's going to slow down when we get into things that are not a vacuum, Ralph put in the chat, because some of the light is absorbed into the object. If it might be absorbed, but even if it's not absorbed, just think about this. Suppose that light is an object. Okay, so here is a chunk of light and it's moving. In a vacuum, there's nothing to get in the way. If instead it's passing through air, it's going to interact with the air molecules. And some of the energy is going to get lost in its interaction with those molecules. Well, that loss of energy, that's going to be seen as a decrease in speed. Right? So if you've got something like air, you should figure air is not going to slow down light a lot, because air is not very thick. The molecules are pretty spread out because it's gaseous, right? As opposed to if it was going through water or glass or a diamond or anything else that's kind of clear, so that we can actually see it, that it would actually propagate through. But it's going to slow down, right? So when we talk about the speed of light and we go to that 3 × 10⁸, just remember that that's in a vacuum, because as soon as we're not in a vacuum, we're going to lose some of the energy, right? We're going to lose some speed. And you're right, Victor, a little bit of the light does get reflected, and we'll talk about that quite a bit here in just in a minute. All right, so to help us out, what we're going to do is we're going to create this thing that's called an index of refraction. That's going to be just a measure of how fast light is moving in your material relative to moving in a vacuum. All right. So let me go hop up to the whiteboard because I want to start writing some stuff down. So I'm going to be right back with you in just a second. All right, so let's just start putting some things down that we know. So in the vacuum, the speed of light we're going to use the letter C. So I don't know if you remember this, but in case you don't, we use the letter C, and it's going to be about 3 × 10⁸ meters per second. But as soon as we put it in another medium, it's going to slow down. So what we do is we create this thing N, and what N is going to be is the ratio of the speed of light in a vacuum to its speed in the medium. Okay, so in this case, v, this is the velocity of light in this new medium. So if we were to watch how fast light was traveling through water, when we get that velocity, we would divide that into c and create this guy n. So n, this is called the index of refraction. We'll talk about why it gets that name in a minute. We got to talk about refraction before we can see what that is. All right. And again, this is dependent upon the material. So different materials have different n values. All right. So if you look in a book, like this book has one, almost every physics book is going to have a chart of n values for different materials, right? Let me give you some of the more common ones. These are objects that you know about, you experience, that you've seen, so you can see what they are. So air, its n value is like 1.000293. So notice that it's just slightly bigger than 1. All right, well, let's just think about how that n is going to form and what that means in terms of the velocity in air. First of all, n is always going to be bigger than 1. It's going to be at least 1 because speed of light in a vacuum is greater than any other velocity. So it's always going to be at least 1. The bigger it is, the smaller v. So as an object slows down, its n value is going to increase from 1. So the fact that air's n value is very close to 1 means that light doesn't really slow down much in air. The speed of light in air in the atmosphere of Earth is smaller than out in the vacuum of space, but not by a lot. Okay, so it's actually very close to 1. Water. And water, you got to be kind of careful depending upon what kind of water. This is just fresh water, just plain old water, nothing else in there. You go to ocean water, now that it's got, minerals in it. You go to like pond water where there's stuff growing in it. That's not what I'm talking about. I'm talking about just plain old water. Water's n value is right around 1.333. All right, so it's a little bit bigger than air, which means that light is going to travel slower in water than it does in air. But that should totally make sense. Right? Like, think about it. Water has a lot more, in terms of a lot more matter in it. They're bonded together differently, right? Air, there's not a lot of bonding going on between the molecules. So it kind of makes sense that it should slow down in water. Well, check this out. We can actually see how fast it's traveling if we use this formula. Let's just do that real quick. Let's see what kind of speed that gives us in water. So if we go to 1.333 is equal to c over v, then that velocity is going to be c over 1.333. Now that's around 4/3. Dividing by 4/3 is the same as multiplying by 3/4. So in water, the light is traveling at about 3/4 the speed that it would have out in the vacuum of space. So that's a 25% cut. And a 25% cut brings that n up to 1.33. All right, so there's water. Glass. This is one, glass is really weird because it depends on what kind of glass you've got. So I'm going to put an approximate here because it really depends. But it's usually around 1.5, plus or minus a little bit. And so if you kind of do the same thing that we just did with the water, you'll see that for glass, the velocity in glass is about 2/3 that of c. So if you take c and you divide by 1.5, it's the same as getting 2/3. So it moves even slower in glass. All right, well, let me give you another one. Let's look at a diamond. For a diamond, the n is around 2.4. So again, bigger n means it's going to be traveling slower in a diamond. If we kind of go instead to that's around 2.5, just because it makes the numbers a little bit nicer. This means that the velocity in a diamond is about 2/5. Let's see. All right, so that's what we're going to use this n for. This n is just going to be a way for us to know how fast the light is moving in that medium. And it just makes it a little bit easier than trying to deal with the actual speeds. We can get the actual speeds if we want just by using this formula, but instead it's just a ratio. It's the ratio of speed of light in the vacuum to speed of light in our material. All right, well, obviously n's can get even bigger than 2.4. And I do know that scientists have slowed light down to a walking pace. Obviously, the material that they created had to be such that it really interfered with the propagation of light. But in a lab, they've been actually able to turn on a light and watch that light move through the medium at a walking pace.
That would probably be so trippy to see.
I think that would be way cool to see, because we're not used to that, right? We're used to you turn on the flashlight and immediately the light is in the entire room, right? But obviously it's going to be a different kind of material, some sort of weird matrix of gaseous elements or something. But yeah, kind of cool. All right, so we're going to use this n a lot. So make sure you kind of remember this, put a little box around that. And remember what it is. It's the ratio of the speed of light in the vacuum to the speed of light in the material that we're working with. All right, now, for the most part, especially when we're doing all this geometric optic stuff, we're going to treat light as rays. Meaning, imagine that you were to turn on a light bulb here. So we'll draw an old school light bulb. Right? The light is going to come out, going in all directions in rays. Okay. So we're going to treat light as if it's traveling in the direction of an arrow. Think of it like a laser beam. right? You turn on a laser, if there's dust in the air or whatever, you'll see that beam going nice and straight. It's following a ray. Okay, so what we're going to be doing, especially in this first chapter, is just looking at light as a ray. I know you guys probably know, well, actually you definitely know because you talked about it last time. Light isn't exactly a ray. It doesn't follow like it's just moving like a BB or a bullet. There's some waveness to it. We'll deal with that. As we progress, we'll see that we actually have to treat light as both, as if it's moving like a bullet following an arrow, and also like a wave. But for right now, we're going to be looking at this as if it travels in rays. Okay, so the first thing we need to talk about is reflection. So here's the deal. When light hits a surface, it's going to reflect. At least some of it is going to reflect. And what's beautiful is we know exactly how it's going to do it. Let's say that this is our surface. Pick your favorite kind of surface. It doesn't really matter. But the light is going to come down here and hit it. Now, we're going to define the angle from the perpendicular, this guy right here, this is the angle of incidence. Okay, so always when we're talking about light, the angle that's coming in, it's the angle of incidence, and it's always relative to the perpendicular. Okay, so if it's coming straight in, so if it's coming perpendicularly, the angle of incidence is 0. If it was coming parallel, the angle of incidence would be 90 degrees. Okay, so the angle of incidence is always between 0 and 90 degrees. Oh, don't tell anyone I'm using degrees. Let's just keep that between us, all right?
It's being recorded, Bruce.
Damn it! All right, that's it. I'm screwed. All right, so but I'll go to radians. Don't make me. All right, and this is why I badmouth physicists a little bit, because they still haven't gotten on board. I mean, they figured out the metric thing, so kudos there. But anyway, so angle of incidence. Now, when it bounces off, it's going to come off at an angle, and that angle, I'm going to change colors here, even though the light's probably not going to change colors. I'll come over here. I'll make this guy a phi. And this one's the angle of reflection. Obvious enough, right? So you got an angle of incidence and an angle of reflection. Well, it turns out that from many, many experiments, doing many, many times, it is quite clear that these two angles are equal. All right, so the angle of incidence equals the angle of reflection. And this is actually really easy to see. In fact, I wouldn't be surprised if some in lab, Kathy has you do this, where you can shine a light beam at a surface, at a mirrored surface, and you can actually see the reflected beam and measure the angles, and you'll see that they are the same. All right, so the angle of incidence is going to equal the angle of reflection. All right, so if you have a nice smooth surface, What's great is if you were to send in a bunch of parallel rays, they're all going to bounce off parallel to each other, and everything's going to be nicely reflected. But in reality, that doesn't happen very often, right? Like, think about this. I don't know if you guys have any kind of a nice like flashlight handy or something, maybe on your phone, but shine your phone off of a nice smooth surface, like a mirror, piece of glass, something like that. And then hold up, and do this in the dark. It works a little bit better. But then hold up like a piece of paper, right? So you shine your light down on a surface, bounce off, and you will see if it's a good surface like a mirror or a piece of glass, you'll see that light come and pretty much just light up one spot on your paper. But then do it on something that's not super smooth, like a piece of paper, a book. I mean, you want to do it on something really bad, do it like on a piece of carpet or something, on a rug. And that light will not show up in a nice little beam. It'll be really fuzzy, spread out, all that kind of stuff. So in reality, we don't always get nice, pretty picture of one ray coming in and bouncing back. But that's because if you were to really look closely at a surface, I'm going to exaggerate this, but if you were to look really closely at a surface, right, it's going to look more like, well, you guys can't even see that, but we're just do, hold on, let's make it a little bit darker. Right, it's really going to look more like this. Like I said, I'm exaggerating. But now let's send in a bunch of parallel beams. Okay, so here's a light beam that's coming in. Here's another light beam that's coming in. Let's do another one here. Okay, pretend that those things are parallel to each other, right? So we're going to bring in all these light beams. All right, now let's look at see what happens to each one of them as they bounce off. So we know that the angle of reflection is equal to the angle of incidence. So if we take one of these, like let's take this one that's over here. Here's a tangent line to the surface, which means we need to have its perpendicular. So it would look something like that. Now, the angle of incidence is very small, so the angle of reflection is also going to be very small. And it's going to do something like that. All right, now let's come up to this next one. The tangent line to the surface here looks like that. So the perpendicular is like so. The angle of incidence is much greater, which means its angle of reflection is going to be equal to that. So it's going to bounce off sort of like that one. Now, notice that these two are not even close to being parallel, right? Not even remotely close to being parallel because of the fact that they were hitting portions of the surface that were not parallel. All right, well, we can continue doing this. Let me just do one more. So there's that guy, that one. If I bounce that off roughly like this. And so on and so forth. So what's happening now is instead of getting them all going the same direction, they scatter, right? They start going in all kinds of weird directions. And we call this diffused reflection. And diffused reflection is actually a really good thing. And let me explain why. All right, so you guys all see this, right? You can see this cardboard with the back of my notepad. The reason that we see anything is because the light is bouncing off of it and coming to our eyes, right? This kind of goes back to what Victor was talking about when I said talking about light. He said, well, it lets us see things. The only reason you see anything is because light is coming from that object. Now, you're looking at your computer, that light is being projected towards you, so it's a little bit different. But if you're not looking at the thing that's producing the light, so think about your table, right? The table that the computer's on, the walls in your room, clothes, right? Anything like that. The only reason I can see this shirt is because light is bouncing off of it into my eye, right? Okay, now imagine that we had a perfectly smooth surface and I have a single light source, one light bulb. That light's going to come, hit that surface, and then bounce off in just one direction. And the only way I would be able to see that light is if I happen to be where that bouncing ray went. All right, well, because this surface is not smooth, some of that light hits and bounces into my eye, so I can actually see it. A great place to see this phenomena in real life is with your car and headlights. Okay, so think about driving at night when the road is dry. You know, it's just a nice night, and you've got a black road, but you can still see the road pretty well, right? Your headlights, the light is bouncing off that roadway. Lots of it is coming back into your eye, so you can see that road. Okay, now picture in your mind when you've gone out when it's really wet or icy. Let's go to wet. So that water is going to fill in all the little grooves in the road and is going to make it so that you've got a nice flat surface. It's actually much harder to see the roadway when it's wet because the light from your car is hitting that surface and bouncing away instead of coming back to your eye. Right? So we actually make use of diffused reflection. It's one of the reasons why we can do what we do. But in certain circumstances, we don't want that, right? We want like perfect reflection. But perfect reflection is, it doesn't happen. You know what I mean? It's the optimal, but in reality, nah, you're actually going to get some diffused reflection. But regardless, it's all because light reflects off the surface at the same angle at which it comes in. All right, so it's kind of a cool feature, whatever angle we're coming in, at least. Now, there are things that we've created to make use of this that are very practical. And one that we use a lot in the everyday world are what we call retro reflectors. So retro, that means to return. So anytime you see the word retro, it means to return. Even if we talk about, you know, like clothes that are retro, because they're back in style, that style has returned. Okay, so anytime you see retro, that just means to return. So a retro reflector is a reflector that returns the light. Well, check this out. This is kind of cool how this plays out. To create a retro reflector, all you need are two mirrored surfaces that are at right angles. Okay, so here's our right angle. Because watch what happens as we send in a ray. Okay, so we're going to follow this. It's going to bounce off into the second surface, and then it's going to bounce off again. But just follow the angles here. Let's do a little geometry. All right, so I'm going to call this guy theta. Well, that means that this one is theta because the angle of reflection is equal to the angle of incidence. All right, well, let me put in another perpendicular at the other surface. Now, this perpendicular and the mirror on the bottom are parallel to each other, which means from geometry, I know that this angle is also theta. All right, well then, since this is reflecting off the second surface at the same angle, this is also theta. So check it out. That means that these two are parallel to each other. So this is just geometry. So if you have two reflected surfaces that are perpendicular, anything that comes and bounces off one of them into the other is going to return parallel how it came in, which means it's going to be coming back towards the source. If you wanted to do this three-dimensionally to make sure that it was definitely going to reflect off, you just create a third dimension, put a third mirror so that it's kind of like the corner of the room, so that all three of them are parallel to each or perpendicular to each other. And that one, no matter how you shine light in, it's going to come back the same direction that it started. So that's why it's called a retro reflector, because it's going to reflect return to where it started. Okay, so I said we use these a lot. Can you think of a place where you've seen in the real world where you send light at something and it returns back to you?
Reflectors on the road.
Yeah, it's a great example. There are tons of these in driving world. But yeah, the reflectors on the road, the ones that are on the side of the road, the ones that are in the road, right, that reflect certain colors. Or how about this? Think about street signs. Have you ever noticed how much brighter street signs are than the surroundings when it's dark? I don't know.
I always thought it was just the material.
Well, I mean, it is. But that material has in it a bunch of little retro reflectors. They're designed in such a way that as the light hits, they bounce right back at you. And so it's going to appear much brighter, right? Like, let's say this whiteboard had this region that was painted with retro reflective stuff, and this part that isn't. This part's going to bounce right back at you. The other part of the whiteboard, some of that light's going to come back at you because of the diffused reflection, but there's going to be a lot more that scatters in all kinds of different directions. All right, well, that's why that stop light or stop sign really shows itself when the telephone pole that's right next to it doesn't. Right, so lots of things are designed that way, like reflectors on bicycles, you know, those little plastic reflectors that are like in the wheels and stuff. Those have retro reflectors built in so that the light comes in and bounces straight back. The Apollo 11 guys, when Armstrong and Aldrin were on the moon, they actually put down a retro reflector that we still use today to measure the distance to the moon, because you can aim a laser at it. Because it's a retroreflector, it's going to bounce back. You can time it, and then, you know, because we know the speed of light, it gives us an idea of how far away the moon is. So anyway, retroreflectors are out there. All right, so reflection. That's one of the things that light's going to do. Anytime it hits a surface, it's going to bounce off. And it's going to bounce off at exactly the same angle. All right, so that's reflection. Now, the other big thing that light does is it refracts. So let's talk a little bit about refraction. And I apologize, it's not me, it's just the physics world. We have reflection and refraction. They sound very similar, they look very similar, but they're very different. All right, so gonna make sure we keep them separate. But here's what refraction is. Now, suppose that we've got a surface that allows light to pass through it. So a window, top of a lake, something like that, right? When light comes in, it's going to come in at some angle relative to the surface, right? And so for this one, let's call its angle of incidence θ1. So I'm going to put a perpendicular here. And we'll call this guy θ1. When it passes through this surface, it's going to bend. And I'm going to exaggerate the bend. Okay, so something like that. And it's going to come through at a different angle, potentially, than it came in at. Okay, so we're going to call that guy θ2. And this is refraction. The light actually bends as it passes through this interface between media. All right, the light's actually going to bend as it does this. And this is what we call refraction. All right, now those angles, θ1 and θ2, are related to each other. Okay, they are definitely related to each other. And they depend upon what the media are, what these things are. Now, what we're going to do is let's just say that this first medium has an index of refraction of n1. Okay, so you remember that n, like water's was 1.33, diamond was 2.4, right? That's what this n is. That's just going to be the n of this material. And then the second one, we'll say, has n2. Well, it turns out that these angles are related to each other by this thing called Snell's law. Snell was a Dutch physicist who figured this out experimentally. And what Snell's law says is that those angles are related to each other by this formula right here. That n1 sine θ1 is equal to n2 sine θ2.
Do you know why they use sine instead of cosine?
Yes, because it's how it has to play out. Because cosine, like if you did n1 cosine theta 1 and n2 cosine theta 2, it's not the same as with the sines. It comes from the geometry. So I guess the reason why is it sine, because it has to be. If you use cosine, it doesn't work. All right, so this is Snell's law, and this is definitely true. This is definitely how it holds. But I want to just I want you to see kind of what happens with this. We'll do some numbers. We'll run some examples. But this is good old Snell's law. All right, so basically, if you want to know what's going to happen to light as it's going from one medium to another, you need to know what mediums are they? Like, what are the n values? What are the indices of refraction? Oh, by the way, that's why the n is called the index of refraction, because it has to do with refraction. So you need to know those n values, and you also need to know the angle at which it comes in. So here's an example. All right. So suppose that we're going to go from air to water. So a great example would be Lake Tahoe. We're going to shine a beam of light, like we're going to take a laser and we're going to shine it at the surface of Lake Tahoe. Some of that light will reflect off, but some of it will also pass through and it will refract. Okay. And suppose that we know we're going to put here at an angle of 30 degrees. And when I talk about the angle here, I am talking about an incident angle. We'll write it that way, into water with an incident angle of 30 degrees. Here's my question is, what is the refracted angle? Okay, so refracted angle, what's the angle we get after it refracts? All right, so we're just going to go to Snell's law. It's pretty easy. So we've got n1 sine theta 1 equals n2 sine theta 2. We want to know theta 2. So let me just solve this. So sine of theta 2 is equal to n1 sine of theta 1 over n2. All right, so we're going from air to water. I'm just going to call n1 1. In general, when we do our calculations, it's going to be totally fine for you to take air and say that its n is equal to 1. We know that it's not exactly equal to 1, but it's so close to 1 that it's not going to really change our angles all that much. Like when we do these calculations, we're going to have bigger issues with other rounding than this. Okay, and then for water, let's just go with fresh water. So we'll go n equals 1.333. So we're going to get 1 times the sine of 30 degrees divided by 1.333. All right, so it's easy enough. We can just do an inverse sine, and we'll get our theta 2. And I just realized that I left my calculator in the other room, so I can't do this real quick. I'm good, but I'm not that good. So if anybody's got a calculator handy, make sure you're in degree mode. Anyone tell me what this is? What kind of angle you get? It's the inverse sine of 3/8. Is everybody else has?
I got 22.1 degrees.
All right, that sounds about right. All right, so there's our answer. We came in at 30 degrees and we're refracting at 22.1. So again, remember that these are angles relative to the perpendicular. So let me see if I can actually draw this kind of decently for our picture. So we came in at 30 degrees. That's probably 30 degrees or close enough. And then when it refracted to 22.1. So here's what happened. As it went from air to water, that light bent towards the perpendicular. It got more up and down. And that's what's always going to happen when we go from smaller end to bigger end. Just look at this formula. Right? If n gets bigger, that means the sine of theta has to get smaller. Right? There's that balance. So if n goes up, sine of theta goes down. Well, if sine goes down, the angle goes down. So whenever we have light that's going from smaller end to bigger end, it's always going to end up getting a smaller angle. And the reverse happens. If we go from smaller end to, or from bigger end to smaller end, it's going to actually refract away from the perpendicular. It's going to bend away from that line. All right, so the calculations are easy. It's not really that big of a deal. It's just a matter of knowing what is it that we're in. But this is a pretty easy case, right? Just water straight from air. So let's change this a little bit. Let's put another material here. So this time, let's go from air into glass and then into water. Right? So this would be like an aquarium or a glass of water or something like that, right? So let's add in one more layer. So this is what it's going to look like now. We're going to have air, glass, and then water. So the various n's, again, for air, we're going to let n equal 1. For the glass, let's use 1.5. And for the water, let's use 1.333. And we'll still come in with that same angle of incidence of 30 degrees. All right, well, really, this isn't that big of a difference. It's just we have to do 2 steps now. Right? So let's think about first, how's it coming? What happens as it passes through the glass? We can actually use the same formula right here. If we think of it as it's coming into air and going into the glass. Let me draw some orthogonal guys here. So this is going to be our 30 degrees. And the question is, what is that angle right here? All right, well, let's calculate. So we're going to have sine of theta 2 is equal to 1 times the sine of 30 divided by 1.5. So notice the only thing that I changed was N2 because we're going from air to glass now instead of from air to water. Right? Other than that, the structure is exactly the same. All right, so Bradley, when you get a theta 2, can you tell me what it is? Or if somebody else beats him to it, that's all right too.
Uh, 19.5.
Okay, cool, thank you. So it's a little bit smaller than what we found the other time, which should make sense, right? Because we've gone to a bigger n. Bigger n means smaller theta. All right, so that's what happens once we come out of the air and into the glass. So this is 19.5 degrees. Well, now let's go into the water. So I'm going to put another orthogonal thing here. So in terms of the formula, it's going to be the same kind of formula. It just now it's going to be sine of theta 3 is going to equal n2 sine of theta 2 over n3. So n2 was 1.5. n3 is 1.333. So those are the n values. But I need to know the angle of incidence of that ray when we're going from glass to water. So we got to be kind of careful here because the angle that we just calculated, let me actually move it here, was this one. But what I need to know is the other guy, right? This is actually my theta 2.
It's the same, right?
All right, is it the same?
I think so. 'Cause alternate interior angles are congruent.
Yeah, it absolutely is. Because both of these are parallel to each other because they're orthogonal to the surface. So it turns out that that is the same 19.5. So this is kind of nice, actually. If you've got multiple layers that you're going through, multiple media, that's fine. Whatever angle comes out as you're passing through one medium is going to be the angle going in to the next one, assuming the layers are parallel to each other. Right? If the layers were at weird angles, then we'd have to worry about the geometry of it. But if they're parallel to each other, then this is just going to play out. So it's that same angle, 19.5 degrees. All right, cool. So we're at a point now where we can calculate theta 3.
I don't know if this is wrong, but maybe this was your point, 22.1.
Wait, what?
Yeah, I got 22.1 again.
You got the same number that we got the first time?
Yeah. I'll try again though, just in case.
You can try again just in case. Don't bother. No, it is the same. It's absolutely the same. Okay, so now all of a sudden you're like, wait, what? Yeah, it turns out we didn't need to worry about that middle step. the middle step was irrelevant to what angle we got at the very end. Because check it out. Go back to Snell's law. We had n1 sine of theta 1 equals n2 sine of theta 2. But then we also had at the second surface, n2 sine of theta 2 is equal to n3 sine of theta 3. You guys all remember your substitution, right? Since these are the same, you just replace it, and we get n1 sine theta 1 is equal to n3 sine theta 3, which was the same as if there had not been glass there at all. What if there was another layer? Like, what if there was some ice on top of that glass? So we go from air to ice to glass to water.
Won't matter.
Won't matter. It will not change that angle at which we're coming out. So that's kind of a beautiful thing here about Snell's law, is that totally doesn't matter how many layers you have, what the material is. The only thing that's going to matter at the end of the day, where all we're concerned about is what angle are we coming out at, is what angle did we come in at, and what are the very top and very bottom layers. Okay, so did that glass actually do anything? Yeah, it did. It didn't change the angle that we came out, but it definitely shifted where that ray is, right? Like, let's kind of follow this and go to let me extend it back out here a little bit so that this is our 22.1 degrees, right? If instead of going through that glass, if we had gone straight from air to water, so imagine that this middle layer wasn't there, but we just came in at 30 and then left at 22.1, what we're going to see, let me go, I think green, maybe we can see green. Right, it would just gone from this blue to this green, but notice that there is separation here. They've been split a little bit. So that glass is causing the path to be different, even though the angle is the same. All right, well, this is how you do the calculations. Super easy, super easy, super easy. But what does this look like? Well, you've seen this. Have you ever looked at like a straw that's in a glass of water?
Yeah, like it looks like it's in a different spot.
Mm-hmm. Looks like a different spot. Looks like it's bent, right? Like your straw is going and then it turns. That optical illusion is what you're seeing here. What you're seeing, your brain is getting tricked. Your brain is thinking that that straw got bent, when in reality, what got bent were the rays, or the light rays. Because, again, let's talk about what you're seeing. So remember your eye, it's going to see the light wave or light ray, and it's going to interpret it as it's just going to go backwards. It's going to go, oh, that's where it came from. So let's do this sort of the other direction. Let's go from water to air, but let's put something in the water. Okay, so there's going to be a light source right here sending out a ray. So maybe that's the straw So that's a light ray that's coming off of the straw. Now, as it goes from water to air, because water has a bigger N, if it goes from bigger N to smaller N, the angle has to adjust to account for that, right? So if N goes down, theta's got to go up. So it's going to bend further away. So I'm going to really exaggerate it. But it's going to bend further away from the perpendicular, right? Going from a smaller angle to a bigger angle. All right, now your eye is over here. And it sees that light ray. Well, here's how your brain interprets it. Your brain follows this backwards. And your brain is going to think that the object was actually right there. Was actually above where it truly was. That's why your brain goes, ooh, that straw's bent. That's why it doesn't look like the straw is straight anymore. Because the part of it that's in the water, your brain is interpreting as having moved. Because of the fact that the ray gets bent. This is also why pools look shallower than they actually are. I don't know if you've noticed that, but a swimming pool will look a lot shallower than it truly is. Or I don't know if anybody's ever tried to like reach in and grab a fish in the water. Most likely, if you've ever tried to do that, you miss the fish, not because the fish is fast, but because you are above where the fish actually is. You reached in thinking that it was only this deep when it was really further below you. Or, here's another good example. Have you ever been out on the lake swimming? And you're like, oh, there's a really cool rock or something down there. I'm going to swim down to it. And you ever notice that?
And that shit's 20 feet deep.
It's way further away than you think. Same thing. You're seeing it as, oh, it's up here shallow, when in reality, it's further down. So this is a real thing. This is a very real optical illusion that we experience in lots of places. And it's all because of Snell's law. It's all because of refraction. Because of the fact that the light bends, it appears to look different. All right, so it's real. It definitely exists. And you can actually prove Snell's law using calculus. You remember the lifeguard problem? The whole, like, you're going to run part of the way and then swim part of the way. And you got to try to find the point at which you minimize the amount of time to get to the drowning person. You guys remember that one from calculus? Just a real quick thumbs up. Which calc? Would have been first quarter when you optimized. At least Victor remembers. Okay, cool. If you don't remember it, it's one of the classic minimizing time, max min problems. Well, all right, so here's the deal. If you were to say, I want to be at this point and go to some point out here, and you want to minimize the amount of time that it takes for the light to travel, and you run that problem, you get Snell's law. I don't think Snell had calculus available to him yet. But this is one of those things that now in retrospect, you're like, oh, dude, you just use a calculus, you can prove it. All right, but we still kind of haven't gotten to the why does this happen? I mean, I guess calculus proves it if we trust the math. But let me give you kind of an example or a way of thinking about it to show why it has to bend. All right, so this example has nothing to do with light at all. Think about a bunch of soldiers that are marching in nice rows, or a marching band, or insert your favorite kind of formation where you've got a bunch of people that are just sort of marching. And here's what we're going to do. We're going to have an interface where we're going from grass to mud. Okay, so we're looking down on the ground, and there's just a line where we go from grass to mud. And we're going to have a bunch of soldiers or band members or whatever that are all marching in a nice little row formation here. Okay, so that all of them are nicely in line. And those lines are nice and parallel. All right, and they're marching this direction. So they're marching through the grass, no big deal. Everybody's doing great. But then they hit the mud. So what's going to happen to the people that are marching in the mud? Other than get dirty.
It might look like they slow down.
Yeah. And I don't think it just might be. They're going to slow down. You're not going to be able to keep the same kind of pace. Your gait is going to shorten, whatever. You're going to slow down a little bit. Okay, so let's think about this first person that hits the mud. They're still going to go forward some, right? So let's have them go forward like this far. All the other people are going to go much further in that same amount of time. So if you were to look at these, they're still all nice and parallel to how they were before, but now there's a bit of a kink in the path. All right, so in that next amount of time, let's follow now, we've got two people in the mud. So this one does his same step forward. This one does a step forward. This one reaches the mud. This one's not there yet. And if we look at this now, the ones that are still out in the grass are all nice and parallel. And these guys are in line, but in a different line. Is that right? Right? And we continue the process. And what's going to eventually happen, hold on a second, I need to make sure that's parallel. Yeah, okay. Those last two lines were crappy, so let me just do this. So that's parallel and turned, and then finally parallel. All right, so check out what happened. We went from having a row that was oriented this way to one that's now oriented this way. So it turned. Okay, well, think about these as the wave fronts for light. These rows are the wave fronts. Those are perpendicular to the direction of travel. So this light ray would have been coming in this direction, but it's going to go out in this direction. And if I put the perpendicular on there, so that we can kind of compare it to what we just did before. And I'll erase a little bit here. So here's our theta 1. And there's our theta2. And you can see that theta2 is smaller than theta1 because we're going from smaller n to bigger n. Bigger n means you slow down. We're slowing down in the mud. So this is analogous to what happens as those waves, those light waves, come to a surface. The parts that have passed through slow down. That causes eventually these wave fronts to bend. All right, so you don't actually need calculus to see why it happens, because we have other physical examples where this occurs. But it definitely works this way. All right, so there's a little bit with Snell's law. Let's do this. Let's do another example where we're going from bigger n to smaller n. So we're going from where we travel slow to where we travel quickly. But let's really exaggerate it. Let's go to diamond. All right, so here's what we're going to do. Let's go have light going from diamond into air. And let's have an incident angle of 10 degrees. And same question, what's the refracted angle? So good news here. Nothing changes. Absolutely nothing changes. It's still Snell's law. We're still doing n1 sine theta 1 equals n2 sine theta 2. It's just we have different n values. Right? So now the diamond, that's n of 2.4. Again, air is n of 1. So if we go to the n1 sine theta 1 equals n2 sine theta 2, well, now n1 is 2.4, because that was the diamond. We're starting in the diamond. We have the sine of 10 degrees. That's going to equal n2, which is 1, times the sine of theta 2. So exactly the same idea. All right, so theta 2 then is going to be the inverse sine of 2.4 sine of 10. And Bradley or whomever, somebody can get me that angle. I can tell you this much. I know it's going to be bigger than 10 degrees.
Yeah, 24.6.
24.6. Cool. Thank you. Thanks, Victor. Okay, so it went from 10 degrees to 24.6 degrees. Okay, cool. That makes sense. It should be bigger because we're going to smaller n. We're going the opposite direction. So it came in at 10 degrees and it left at 24.6. So if this is our picture, it came in at 10 degrees and left at 24.6. Right, there's our diamond. And there's our air. All right, so real quick, this should be easy to do because in your calculator, everything is exactly the same. Instead of 10 degrees, change that to 70. What happens if that's actually 70 degrees instead of 10 degrees? So I'll change this to 7. And this one to a 7. What kind of angle do you get now?
Domain error.
That's not an angle. Your calculator just said domain error.
Yeah.
Okay, that's never good. So Victor, you got a number for us last time. You have a similar issue?
Yeah, I have an issue.
Okay. All right, so evidently I broke physics by changing that angle to 70 degrees. Now physics doesn't work anymore. Okay, well, I can tell you mathematically what's happening. When you take the sine of 70 times 2.4, you get a number bigger than 1. And we have a problem with sines being bigger than 1. I mean, okay, it's not a problem if you allow yourself to have complex angles. Right, so there's a bit of an issue here. All right, so evidently physics doesn't work anymore. Well, that's nonsense. We can't have that. Physics still has to work. So the question is, what's going on here? Well, let's kind of draw that picture again. So here's our surface. Now we've got an angle of incidence of 70 degrees. So that's like this. And what's happening on your calculator is you're not getting an answer. You're not getting an answer whatsoever. Well, let's think about what would have to happen. We know that that angle has to get bigger, right? It has to increase. So it has to refract away further away. Well, here's the problem, is that if we do this, if we just start increasing the angle, right, we're going to increase the angle of refraction until eventually the angle of refraction gets to being over 90 degrees. And that's a problem. We can't actually have that happen. So what's going on in this situation? If we're coming in at 70 degrees, there is no refraction. So what happens with this light beam?
It probably just lights up the surface and doesn't go anywhere.
Okay, so it doesn't pass through, right?
Yep, you see it.
It doesn't pass through. But we also know what's going to happen if it hits a surface, it's going to reflect, right? So what's going to actually happen here is it's just going to reflect. It's not even going to light up the surface. I mean, maybe just locally a little bit. And that's going to be because this is the real world and it's not just a hypothetical, right, deal. Like this is perfect in the theoretical world, right? In the real world, we have other issues. But in this case, it just comes right back. And this is what we call total internal reflection. This is where physicists start talking like mathematicians. It's exactly what it sounds like. It's total reflection inside the material. It doesn't actually get to leave the material. So if we had, let's say this is a laser that we're shooting from inside a diamond, if it came at 70 degrees, all of that light would stay inside the diamond. All right, this can always happen when you go from bigger N to smaller N. Okay, so I'm going to put this can happen only when going from bigger to smaller N. So like when we are going from air to water, that will never occur. Because when you're going from smaller to bigger N, you're decreasing that angle. Decreasing that angle means getting closer to perpendicular, which is not going to ever be a problem. It's when we increase that angle that we can increase far enough from perpendicular that it's too far and it won't work anymore. All right, so believe it or not, this is used all the time. You guys heard of fiber optics?
I've heard it, but I don't really know what it means.
Yes.
Okay, so you've heard of fiber optics, and they use it a lot for telecommunication cables. You know, your fiber optic cables, and what fiber optic cables are made out of are little tubes of like plastic or glass or something like that. And what they're really good at is making use of total internal reflection to make sure that all of the light that passes through that little tube ends up on the other side. All right, so think about this. Suppose that this is a little tube of fiber optic cable. And what I'm going to do is I'm going to send a signal through it as a light pulse. So I'm going to send in light like that. If the N is big enough, I'm going to get total internal reflection. It hits the other side, total internal reflection hits the other side, comes out. So I started with my signal here, and it shows up on the other end. So if this was like a little cable, or a little like glass tube, basically if I shine a light on one end, even if that tube cable moves and twists around, on the other end, you're going to see that light come out. And yeah, one of the biggest uses is with data transmission, because you're not going to lose your signal as it goes down this wire. There are all kinds of physical examples. If we were together, I have the coolest mineral sample. You know what I'll do? I'll take it down to Kathy's office. She'll never find it in mine. I barely know where things are in my office. I'll go bring it down there so she can show it to you in lab. Its non-technical name is called TV stone. It's actually called, it's ulexite is what it is. But it's natural fiber optics. And it's really kind of cool when you set this thing on top of like a piece of paper with writing on it. I don't want to spoil it. I'll let you just experience it. But I'm going to pass that on to Kathy. I don't know when I'm going to be on campus next, but hopefully sometime soon I'll run up there so that she can show this to you. Because it's pretty cool that fiber optics, even this total internal reflection, occurs naturally. You can also see this. I don't know if anybody's got an aquarium, but you can see this in an aquarium really easily, a fish tank. If you're looking at a fish tank, sometimes when the angle gets just right, you can't actually look through the fish tank anymore. What you're seeing is like a reflection of the other side inside the fish tank. That's another place where you'll see natural total internal reflection. All right, so here's my question now. Like with the diamond to air, we saw that 10 degrees was no problem. It refracted through, everything was great. 70 degrees led to total internal reflection. Where's the cutoff angle? Like where is the place where we go from not being able to, or from having light refract through to the point of total internal reflection? So that's what I'd like to figure out. At this diamond air interface, what's that angle where we change from being refraction to internal reflection? Well, to answer that, let's look at the refraction angle, because kind of the sweet spot is going to be here, where we got this thing, and the refraction is such that we're just pretty much coming along this line. Right, so we're coming in, and the refracted angle, it's been getting wider and wider and wider until eventually it just comes like that. So in essence, I need θ2 to be 90 degrees. So what is this θ1 then? Okay, well, if we set this up, n1 sine θ1 is equal to n2 sine of θ2. I want θ2 to be 90 degrees. Well, the sine of 90 degrees is 1. So we get sine of θ1 is n2 over n1. So that angle, which is going to be the biggest angle we can use before we get total internal reflection, is going to come from this formula right here. It's going to be the inverse sine of n2 over n1. Get my shadow out of the way. And this is, we call this the critical angle. So if your angle is less than that, you're going to get refraction. If it's greater than that, you're going to get total internal reflection. So let's check it out for diamond to air. Okay, so let's go with the diamond to air interface. Here's our critical angle. So I'm going to call it θc for theta, for angle critical angle. It's going to be inverse sine of 1 over 2.4. Because again, n1 and n2, n1 is where we are, we're in the diamond, n2 is where we're going, it's the air. So it's inverse sine of 1 over 2.4. All right, so calculator people, get me an angle. I know it's somewhere between 10 and 70. I actually know that it's less than 60.
24.62.
24.62.
Yeah.
Wait, didn't we see that number before?
Yeah, that's what we got before.
Oh, but that was the angle that came out.
Mm-hmm.
Oh yeah, that's just coincidence. That's totally just coincidence, by the way. That's weird that I picked that number then. All right, but I definitely agree. It should be less than 30 degrees because 30 degrees, the sine of 30 degrees is 1/2. Half of 2.4 is still bigger than 1. All right, so just think about this. As soon as we get more than 24.6 degrees off of perpendicular, those rays are going to be totally internally reflected. So because of the big difference in N, diamond tends to trap light. Well, you know how diamonds are real sparkly? This is one of the reasons why. We'll talk about the other reason why next time. I don't think we have time to get to it today. But total internal reflection is definitely part of the reason that diamonds are very sparkly. All right, so again, this is just another consequence of Snell's law. It's just in this circumstance when we're going from bigger N to smaller N, that can happen. We can get total internal reflection instead of refraction. All right. I think I'm going to call it a day because I see on my clock it's 6:10. I don't really want to get into the next topic because it's going to be more than 10 minutes long. We're in fact, where we're going, what we're going to talk about starting next time is rainbows. Why rainbows happen, why we see all those pretty colors, all that kind of stuff. So that's your hook for next time. In terms of other stuff, you could probably make good headway on homework 1. A lot of what we talked about has to do with reflection and refraction. The math on it's going to be easy. There's just a couple of formulas. It's going to be more the thinking about it, making sure you got everything set up right. That's going to be the challenge, but I think you guys are probably used to that now with physics, is that the formulas themselves are not that hard. It's just a matter of applying them properly. All right, so I guess with that, we'll call it a day. I'll see everybody on Thursday. Hope you have a great couple days. And as always, don't hesitate to reach out if you have any questions. All right.